Have you ever pondered what would happen if you could tunnel through space-time? Imagine a universe where distances that took light years to traverse could be covered in the blink of an eye. This is the tantalizing promise of wormholes. Wormholes, in theory, are tunnels in the fabric of space-time. Picture an apple and a worm burrowing its way from one side to the other. The worm could travel over the surface, a long and arduous journey, or it could bore straight through the middle, a shortcut. Wormholes are the cosmic equivalent of that tunnel, offering a potential shortcut through the vastness of space. But what exactly are these theoretical tunnels? They are solutions to the equations of Einstein's general theory of relativity, the same equations that predicted the existence of black holes. However, while black holes are a reality, confirmed by countless observations, wormholes remain firmly in the realm of theory. So, how are wormholes different from black holes, you ask? Well, black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. They are cosmic dead ends. Wormholes, on the other hand, are conduits, a theoretical passage through spacetime that could potentially link two distant regions of the universe. They're not a trap, but a gateway. It's essential to remember, though, that wormholes are purely theoretical at this point. They exist on paper, in the complex equations of theoretical physicists, but we've yet to find any empirical evidence of their existence in our universe. That said, the idea of wormholes has far-reaching implications. If they do exist, they could provide shortcuts through spacetime, allowing us to reach distant parts of the universe in less time than it would take light to travel the same distance. Imagine the possibilities for interstellar travel, for exploration, for understanding our universe on a deeper level than ever before. So in essence, wormholes could be the universe's very own cosmic shortcuts. Fascinating, isn't it? Now, you might wonder, who came up with such an extraordinary idea? Enter Albert Einstein, a renowned physicist and mathematician. His groundbreaking work in the early 20th century has shaped our understanding of the universe. The theory of relativity, one of his most significant contributions, has played a pivotal role in the concept of wormholes. Einstein's theory of relativity consists of two parts: special relativity and general relativity. Special relativity, formulated in 1905, introduced us to the idea that the laws of physics are the same for all non-accelerating observers. It also suggested that the speed of light within a vacuum is the same, no matter the speed at which an observer travels. Then, in 1916, Einstein expanded his theory with general relativity, which proposed that massive objects cause a distortion in spacetime, which we perceive as gravity. This revolutionary idea changed the way we perceive the universe and paved the way for the concept of wormholes. Wormholes, in essence, are shortcuts through spacetime. They are solutions to the equations of general relativity that describe connections between different points in spacetime. Imagine bending a piece of paper and poking a hole through it. The shortest distance between 2 points isn't a straight line anymore, but a tunnel through the paper. That's a crude metaphor for a wormhole, but remember, wormholes aren't just tunnels in space, they're tunnels in time as well. This means they could potentially allow for time travel, an idea that has fascinated and intrigued humans for centuries. Einstein's theory of relativity doesn't just allow for the existence of wormholes, it necessitates them. The equations of general relativity predict their existence, although we have yet to observe one directly. Without Einstein's theory of relativity, the concept of wormholes would merely be a figment of scientific imagination. But thanks to his trailblazing work, we're able to explore these fascinating possibilities and ponder the mysteries of the universe. But what if these cosmic shortcuts could do more than just shorten our journey across the universe? Let's dive into the tantalizing concept of time travel. Wormholes, these fascinating phenomena, are not just potential gateways across spatial distances, but they may also serve as bridges across time. According to some theories, if we could harness the power of a wormhole, we could potentially step into a different time altogether. Imagine, for instance, stepping into a wormhole and emerging not just millions of miles away, but also 100 years into the past or future. But here's where things get tricky. Time travel is riddled with paradoxes that can tie your brain in knots. Let's take the grandfather paradox, one of the most famous examples. Suppose you travel back in time and prevent your grandparents from meeting. If they never meet, they never have children, meaning one of your parents never exists, and subsequently, neither do you. But if you never exist, how could you have traveled back in time to prevent your grandparents from meeting? It's a mind-boggling loop with no clear resolution. And then there's the bootstrap paradox, another conundrum. This one involves an object or piece of information sent back in time, becoming the very thing that was sent back in the first place. It's like a chicken and egg scenario, where it's impossible to determine which came first. Yet despite these paradoxes, the possibility of time travel through wormholes remains a topic of serious scientific discussion. Theoretical physicists suggest that quantum mechanics might hold the solution to these paradoxes. Quantum superposition, for instance, could allow for multiple timelines to coexist, sidestepping the issue of causality. In this quantum realm, the laws as we know them could be rewritten, and the impossible might just become possible. So, while time travel remains largely in the realm of science fiction today, who knows what tomorrow may bring? Time travel, once a science fiction trope, could be a scientific possibility with the concept of wormholes. Now don't pack your bags for a time travel trip just yet. While the concept of wormholes and time travel is fascinating, we must also acknowledge the significant challenges that come with it. Firstly, there's the stability of wormholes. Theoretical physics suggests that wormholes, if they exist, are highly unstable. They may open and close so rapidly that nothing could pass through without being torn apart. To keep a wormhole open long enough for anything to pass through, we would need something known as exotic matter with negative energy density. But the existence of such matter is purely theoretical and has not been observed in the natural universe. Secondly, the energy required is enormous. To give you a sense of scale, it's estimated that opening a wormhole just 1 meter wide would require the energy equivalent to that of a star. That's a whole lot of energy we're talking about. And even if we could generate this much energy, we currently don't possess the technology to harness it for creating wormholes. Furthermore, there are several technological limitations. Our current understanding and technology are nowhere near what would be required to create or manipulate wormholes. We're still struggling to reconcile quantum mechanics with Einstein's theory of gravity, let alone manipulate the fabric of space-time itself. But it's not all doom and gloom. Scientists are tirelessly working to unravel the mysteries of the universe. Ongoing research in quantum gravity, string theory, and exotic matter may one day lead to breakthroughs that could make wormholes and time travel a reality, not just a science fiction dream. There's a lot we don't know, but what we do know is that the universe is a vast, mysterious, and exciting place. The challenges are significant, but so are the possibilities. As we continue to push the boundaries of our knowledge and technology, who knows what we might discover? As of now, wormholes and time travel remain within the realm of theoretical physics, but who knows what the future holds? So, what have we learned today about wormholes and time travel? We've dived into the captivating mystery of wormholes, those theoretical passages through space-time that could create shortcuts for long journeys across the universe. We've learned that these curious constructs are not just the stuff of science fiction, but a genuine solution to the equations of Albert Einstein's theory of general relativity. We've also explored the fascinating role that Einstein himself played in this narrative. His groundbreaking work laid the foundation for our understanding of wormholes. The theory of relativity gave us a new perspective on the fundamental nature of space and time, setting the stage for the conception of wormholes and the tantalizing possibility of time travel. Then we took a quantum leap into the concept of time travel. We discussed how, if wormholes are indeed real and navigable, they could potentially be used as a means for time travel. However, we also touched upon the paradoxes that such a scenario could create, reminding us that this is still a very speculative and controversial area of science. We delved into the challenges and possibilities associated with wormholes and time travel. We highlighted the immense technical and theoretical difficulties that would need to be overcome to make them a reality. But we also pointed out the exciting opportunities they could present, from exploring distant galaxies to unlocking new insights about the nature of the universe. Finally, we stressed the importance of keeping an open mind about these concepts. Despite the many hurdles, ongoing research and advancements in physics continue to push the boundaries of our knowledge and understanding. The future may hold surprising revelations about wormholes, time travel, and their place in our universe. And there you have it, a glimpse into the fascinating world of wormholes and the possibilities they hold for time travel. Until next time, keep wondering, keep questioning, and keep exploring the wonders of the universe.